Hey everyone, today I set up a quick and simple test using a NEMA17 stepper motor and a GT2 timing belt. I just wanted to see how a basic belt system runs. So let's first look at the mechanical setup. Here you can see the NEMA17 stepper motor. This one is a 17HS4401. It's a common model used in 3D printers and small CNC machines. The shaft is 5 millimeters in diameter, and I mounted this GT2 pulley on it. I also 3D printed the mounting bracket to attach the motor to the base. Since the NEMA17 front plate dimensions are standardized, I simply used a model from printables. I didn't have to design anything on my own for that. On the other side of the timing belt, you can see the idler pulley. I mounted it on a 3 millimeter shaft, and to hold everything in place, I designed these two small mounts in Onshape and 3D printed them as well. These small collars are also 3D printed. They keep the idler pulley from sliding along the shaft during operation. I tried to make sure that the motor shaft and the idler pulley are nicely parallel so the belt runs straight and doesn't wander from side to side. Next to the mechanical setup, you can see the electronics on this breadboard. The stepper motor is driven by a DRV8825 stepper driver, and I'm using an Arduino Nano ESP32 as the microcontroller. The DRV8825 is a very popular module for this kind of application. The driver gets its logic voltage directly from the Nano, but the motor itself is powered from a separate power supply since it draws much more current than the microcontroller can provide. I also placed the 100 microfarad capacitor at the motor power input to smooth out voltage spikes that can happen when the driver switches the motor coils on and off. Here you can see the 4 wires going to the motor, 2 for each phase. This small jumper connects the reset and sleep pins on the driver. Connecting them ensures that the driver stays awake and operational all the time without needing a separate control pin from the microcontroller. Then we have the 2 key signal connections. One pin controls the rotation direction and the other receives the step pulses from the microcontroller. The DRV8825 also supports microstepping, but I'm not using that in this little test. I'm just running it in full step mode for simplicity. Let's take a quick look at the microcontroller code. Since this is just a simple test and there's nothing performance critical going on, I wrote the code in MicroPython. Here at the beginning, we set up the pins for the step and direction signals. With the Nano ESP32, it's important to remember that the physical pin numbers don't match the ESP's internal GPIO numbers. So, for example, I'm using D8 and D9 on the board, but in the code those correspond to GPIO 17 and 18. The main loop is really straightforward. The motor runs for 4 seconds in one direction and then reverses for another 4 seconds. The stepper moves 1 step forward each time it receives a rising pulse on the step pin from the microcontroller. That's all there is to it. Very minimal code, but enough to get the mechanics moving and test the setup. Now let's power it up and see it in action. I'm running it slowly so you can see how the belt moves. This is just an early test, but later I'd like to combine it with a linear rail and maybe turn it into a small axis system. That's it for this short demonstration. If you have any tips on improving something, please let me know in the comments. Thanks for watching and see you next time.